In the previous chapter, we had a look at the different aspects of protection, at the protection principles. And in this chapter, I will describe how we build up a complete protection scheme based on these considerations. And we will do that in 4 different steps. First is the selection of the main protection, of the short circuit protection. Then we look at the selection of additional protection functions. Third one is additional functions, which are not really protection functions. And then the last chapter will refer to redundancy and reliability. And I will squeeze in a separate chapter on that. For that reason, this chapter on designing a protection scheme is separated into 2 parts. The first part consists of steps 1, 2, 3. Then I will squeeze in a chapter on reliability, and then we will have a look at this redundancy topic, and I will show a couple of examples. So let's start with the first thing. Select the main protection, the short circuit protection. And in order to explain that, I would like to show this diagram. You see here the different areas of application. On the horizontal axis, you see the voltage levels, starting from medium voltage via high voltage levels to extra high voltage, or you can say from the distribution via subtransmission to the transmission level. And on the vertical axis, you see the different components. From the top down, it would be long overhead lines, then cables and short lines, transformers and bus bars. And then I indicate in this diagram what is a typical main protection function in this area. So let's start from the top, from the long overhead lines. You won't normally find them in medium voltage, so you find them in high and extra high voltage application. And in this area, the distance protection is in many cases the main application. You can say nearly on all high or extra high voltage overhead line in the world you find a distance relay. But there is also some overlap with line differential protection, especially if you come one level down to the cables and short lines. You find more line differential protection, or you find both, because I indicate in this diagram with this yellow area there, in the field of extra high voltage line protection, you have typically a duplication of protection. That means there you have either 2 distance protection relays installed or a distance relay and a line differential relay. If we come to cables and short lines and look at the lower voltage levels, at the medium voltage level, then we have the main area of application for overcurrent protection. Again, also with a certain overlap with line differential, depending on the length and on the situation you have there. So you see, it's not an exact definition. If you have this type, you need this type of protection. It depends a little bit on the application. If we look into transformers, on the lower voltage levels, we typically have overcurrent protection or just fuses as protection. If we come to the higher voltage level, the typical main protection against short circuits is the transformer differential protection. And the lowest level here, in this case, the bus bar protection. Bus bars are very important components, so they typically get, especially in the higher voltage levels or in important distribution substations, they get a separate protection only looking at the bus bar. And there the typical protection function is the bus bar differential. If we look at simpler distribution substations, there we need more economic solutions. And one typical application there is the so-called reverse interlocking. That is a special scheme where the overcurrent protection relays, which are available there anyhow to protect the feeders, are connected are connected in an interesting way to protect the bus bar with very short tripping times. So that was the selection of the main protection function, and let's now come to the additional protection functions. You may know in digital protection relays we have the possibility to activate a lot of more functions. In old times you had to install separate relays for all the additional functions. In digital protection relays you have them all together. And what I can do here is I can just explain a selection of additional protection functions which are possible. It always depends on the type of equipment, on the voltage level, and also on the common practice in the company you are working in. And it depends also on sometimes on the country where you are working in, the common practice in the country. The first class of additional protection functions I'd like to mention is the earth fault protection. And in this context we have to distinguish between two different cases. If we have a system where the star points of the transformers are grounded, then the question is, do we need special functions because the overcurrent protection or the distance protection have some sensitivity limits? They cannot catch high resistive faults, and in some areas it may be necessary to install separate protection functions to detect high resistive faults which cannot be detected by the main protection functions. And these are earth fault protection functions in systems with grounded star points. On the other hand, if we have a system where the star points are not grounded, or where we have a Peterson coil installed in the star points, then earth faults are no short circuit. That means our short circuit protection we selected in the first stage does not react at all on any earth faults. That means in this case we need in any case dedicated earth fault functions to detect these type of faults. The good thing here is in these systems we can continue operation because earth faults are no short circuits, but nevertheless we have to detect these faults and we need protection functions. For that we will have a separate webinar on this topic. That means how to detect earth faults in systems where the star points are not effectively grounded. The next point is overload protection. Where is overload protection required? It's mainly for transformers, for motors, and for cables. And the overload protection is basically a thermal protection. It's a protection against too high temperatures. And in the simplest approach, you have a thermal model in the protection relay. You measure the current, because you need the current measurement anyhow for the protection function. And you feed in the measured current into a thermal model of the transformer, of the motor, of the cable, and try to calculate the temperature of the transformer or the cable or the motor. And if you find out a certain maximum temperature could be exceeded, you trip the device. Of course, this is not an exact procedure because, for instance, you don't know the ambient temperature, you don't know the cooling factors and so on. That means you have to do a lot of assumption. If you want to make it more precise, you can also install temperature sensors, for instance, in the transformer and feed that into the protection so you get a more precise estimation of the temperature, and even you can install these things in expected hotspots. And that means you can go closer to the limit. If you don't do any temperature measurement, you have to design the thermal model in a way that you are on the safe side. If you do temperature measurement, you can go closer to the limits. It's important to distinguish between overload protection and short circuit protection. You will see both protection functions have some inverse time curves. But if we talk about overload protection, we typically have much longer tripping times there, as these thermal effects are pretty slow effects. That was overload protection. Another thing I'd like to mention here is the so-called arc protection. We will see that schemes with overcurrent protection tend to have pretty long tripping times for short circuits in the infeeding substations. That means if you have an arc fault in the infeeding substation, the fault duration may be pretty long. And to avoid that, you can add a so-called arc protection, that is a protection function which is based on an optical detection of an arc. That means if you have an indoor substation and you have an arc in the switchgear, it's of course very bright in the switchgear, and this can be detected and can be combined with the current flow, and then you can speed up the protection and can reduce the duration of the short circuit. Of course, you need additional equipment, you need optical sensors, and you need devices who have measurement inputs for these sensors. Breaker failure protection would also be an additional protection function. What is breaker failure protection? Breaker failure protection is a function which detects a situation where a protection relay has detected a short circuit, gives a trip command, but the breaker doesn't work. And this function consists of two parts. The first one is very simple, to detect the breaker failure. You can imagine the protection relay gives a trip command, it sees a short circuit, and nothing happens. And that's easy to detect that because the protection relay sees still current flow, although it has issued a trip command. That means the detection of this situation is normally pretty easy. But then the question is, what are we going to do in such a case? Sometimes it's a possibility to do a retrip on a second coil of the circuit breaker. But if that is not possible, or if that doesn't work, you have to trip all other circuit breakers around the bus bar. That means you need, after you have detected that situation, a wiring that gives a signal to all other other circuit breakers. And you can imagine if you do that for all protection relays, it ends up in a pretty complex wiring. And for that reason, if you have a busbar protection installed there, the busbar protection needs this wiring anyhow. And for that reason, you often have the breaker failure protection included as a bifunction in the busbar protection and not in the feeder protection. Another thing I'd like to mention is the power swing detection function. That is a thing which is important in transmission systems. In transmission systems, especially if you have large systems or if you have weak systems, you may have situations where different areas of your network start somehow with oscillations. That means that the phase angles start oscillating a little bit. And that can lead to strong power flows. These are not short circuits, but that can lead to strong power flows. And these strong power flows can be interpreted as short circuit by the distance protection, for instance. And normally this has to be avoided. That means one application of the power swing detection function is to detect such a power swing and to tell the distance protection, stop, don't react on that, that is a power swing, that is not a short circuit. That means the power swing detection functions are sometimes used to block the distance protection. Another application is, and you can imagine that requires intensive studies of the network, another application is if you detect such power swings that you cut the network at dedicated locations. That means you can also use this power swing detection function to trip the circuit breaker in order to stop these oscillations. And finally, I would like to mention a number of other small protection functions we also sometimes need. Voltage-related functions, or for motors we have some load jam or unbalanced load. Load jam can be, for instance, you have a locked rotor in a motor. Unbalanced load means you have suddenly interruption in one phase. And the last thing I mentioned here is frequency protection. That is often used for load shedding, for instance. Remember, the frequency you have in your system is an indication if generation and load are balanced. If generation and load are balanced, you have a frequency near your nominal frequency of 50 or 60 Hertz. If the frequency goes down, it's an indication that some generation is missing and you have to inject more generation into your network. But you can have critical situation where you suddenly lose a lot of generation because a big power station fails or the network is separated then. And then the frequency goes down very rapidly. And then the only situation to save the system is to cut loads, to come back to a balanced situation with generation and load. And this is done with so-called load shedding functions. And they depend on the frequency. That means we have different set points. If the frequency goes below 49.5 or 49 Hertz, you just switch off parts of the city or part of your loads to save the system, to come back to a stable situation again, and then you have to try to reconnect that. That's normally done just with a frequency protection function, sometimes also with a df by dt function. That means that is a function which reacts on the rate of change of the frequency. So that was a selection of the additional protection functions you may need. And then in addition to that, we have a number of other functions which are not really protection functions, but which are also typically part of a protection scheme. And the first one I would like to mention is the auto-recloser. What is the auto-recloser? The auto-recloser is a function which automatically recloses the breaker after it has been tripped for a short circuit. Why does that make sense? Important thing is it makes only sense in overhead lines. In overhead lines, you have often the situation that, for instance, resulting from a lightning stroke in a thunderstorm, you start a lightning arc between a conductor and the tower. Then you have a situation where you have a short circuit current flowing in this lightning arc, high current flowing there. That keeps the air around this arc hot and ionized, and the current remains flowing, although nothing is really damaged up to now. If you then trip this current flow, the current stops, the air cools down, is no longer ionized, and if you then reconnect the breaker, the system remains in operation. So that's a scheme which is very often used on overhead lines. Important thing, it works only on overhead lines. If you have a fault in a transformer, the chance that you clear this fault by just tripping it and reclosing the breaker is pretty low, also in a cable. So it doesn't make sense. It only gives additional stress to the device. For that reason, it's only applied in overhead lines. And there you can go even one step further. The majority of all the faults are single phase to ground faults. And to clear a single phase to ground fault, it is sufficient to open just one phase of the breaker on both sides of the line. That means instead of opening all three phases on both sides of the affected line, you open only one pole and the other two phases remain connected. And it has significant advantages for this network that part of the line remains in operation during this interruption phase. The point is, if you want to do that, there are two preconditions. On one hand, you need a protection relay which has three different trip contacts, one per phase, and you also need a circuit breaker who is able to do that, who is able to trip single pole. And based on what you have on the circuit breaker side, there are different concepts in use. In many cases, this auto-reclosing function is only initiated in case of single phase to ground faults, which is the majority of all faults, and is then done single phase. If you have circuit breakers who are not able to do that, you have to trip three pole. But there are also concepts in use where you also do auto-reclose in case of multi-phase faults. That means depending on the type of fault, you do either a single pole trip or a three pole trip. So you see that makes the function a bit complicated. There are different concepts in operation depending on type of breaker, on the type of system you have, and the function has to be adaptable to these different concepts. That was auto-reclosing. Then you often have a lot of measurement and control functions available, and that depends on your control concept of the substation. You see, our protection relays do measurement anyhow to do the protection functions, and of course we can also use these measurements and send them via communication to a control center. We also can send any signals up, and we can even receive commands from the control center. If the control center, for instance, wants to trip a line, for instance to do maintenance, we can do that through the protection relay without installing separate equipment for control. And that depends now on the control concept, what amount of functionality is used there. It is typically available in our relay. What is also sometimes there is the so-called interlocking logic. What is that? If you make use of these control functions, the protection relay can not only open and close the circuit breaker, it can also control isolators. For instance, the earthing switch, the line side isolator, the busbar side isolator, all that can be connected to the protection relay. It's not a protection function then, but it can be connected there, and we can do control through the protection relay. And there it is state of the art to have some logic to avoid wrong tripping actions. Just a simple example. You have an earthing switch there. If you want to do maintenance on a line, you open the circuit breaker on both sides, and then you close the earthing switch because you have to earth the line to do maintenance there. But what you have to avoid is that somebody, just by mistake, closes the earthing switch while the line is still in operation, because that ends up in a short circuit. And that is the point where the interlocking logic comes in. That means if somebody gives such a command by mistake, the interlocking logic will block this type of command, because the interlocking logic says the circuit breaker is closed, the line is energized, it's forbidden to close the earthing switch now. So that's one example for interlocking logic. There are a couple of other switching actions which also have to be avoided. That was the field of measurement and control. Another bifunction which is often used is a so-called fault locator. Remember, the principle of the distance protection is we measure the impedance from the relay to the fault, and by that we know more or less precisely where the fault is. We use that to decide, is the fault on the line or is it on the next line? But we can also use it to give this information to the control center. For instance, if you have a 100 kilometer line and after a permanent fault where the auto reclose doesn't help, you must look at the line, you must look what has really happened there. And if you have a long line, it makes some sense to ask the fault locator, what is your estimation where the fault is? Is it at kilometer 10 or is it at kilometer 80? And this is also a little bit a by-function of the distance protection. In our relays, we use separate algorithms for that, because the algorithms used for the protection functions are designed for high speed. They must be pretty fast. And once a protection relay has issued a trip, it takes some time until the breaker opens. And in this time, we can still do measurement. We can do measurement with longer data windows, so we get a more precise measurement of the location of the fault, and this result is then given to the control center by the fault locator. So it's a typical function, by-function of of distance protection. In overcurrent protection, it is only available if you have the voltage. Because remember, to measure the impedance, you need the voltage and the current. That means if you have a pure overcurrent relay or pure line differential relay, you cannot measure the impedance, and then you cannot have a fault locator there. Synchro check is also a by-function which is often used. That is required if somehow the system is separated, you have two parts and you want to reconnect them, and there you may end up in a situation that before you reconnect it, you have really different phase angles or different voltage amplitudes on both sides. And if you have such a situation that, for instance, you have a significant phase angle difference between the voltages, and you then close the breaker, you may get heavy transients, which may end up in an operation of another protection. And for that reason, you often use a synchro check function. That means this function measures or compares the voltage on both sides of the breaker and will only allow the closing of the circuit breaker if the difference between the voltages on both sides in terms of magnitude and in terms of angle is under a certain setting value. That is the synchro check function. Then we need sometimes so-called teleprotection logic. That is a logic which is used together with distance protection. That is a by-function to distance protection to speed up the tripping time a bit. It can also be used for some earth fault functions, also to speed up the tripping time and to get additional selectivity. And the last thing I would like to mention here is a relatively new issue. You find it since decades in many papers, but the area of application is growing. It's the so-called synchrophasor measurement. What is that? That is a measurement of currents and voltages, but very precisely with phase angle and magnitude and a timestamp. That means in this case you need a GPS synchronization in the device. That means you need any access to GPS to provide these exact timestamps, and you do then regular measurement of voltage and currents with a timestamp and send this data to a data concentrator. And if you do that, you are able to monitor transient situations in a system. like these type of power swings I mentioned on the previous slide, they are not visible in the normal operation of the control center. The control center does also voltage measurements, but on a very slow base. You can also only see steady state things there. Here you are really able to measure transients, power swings, and that can be used to get a better understanding of the system, to analyze what has happened in critical situation. And you can go even one step further. You can define, if you detect special situations where you are at the limit of stability, you can initiate some actions, splitting the system or whatever. So that is a new field where the protection function, or where the functionality is not completely in the device. The device is used as a measurement sensor for this function, and the function itself is on a central level in this data concentrator. So that was a look at the additional functions. Of course, it's not a complete list. There are other possibilities. It always depends on the application we have. Now we are through 3 of the 4 steps, and the last step is to look at redundancy and backup concepts. And my personal experience is that discussions about redundancy, reliability of the whole system are very difficult discussions. Because sometimes your stomach feeling on problems lead you into the wrong direction. For that reason, I would like to stop this part here and squeeze in a chapter where I discuss a little bit about reliability issues in protection. That will be the next chapter, and then after that I will come back to this point.